Okay, so let's try expanding on our implementation here to figure out how is it that we're going to add piping. And I've opened up exec.c in my source directory. We know that we're going to need a helper for executing a pipe command. All right, so let's go ahead and add that. And remember, these are structs that their type member will indicate whether or not it's a pipe command or a pipe node or a command node. So each of them expects a parameter type of node pointer. All right. So let's add a case here, and the case is going to be given a pipe node. We're going to exec pipe, right, and give it the node and break. Okay, so we're just going to try and make a very simple extension here, and then see what we run into. And let's go ahead and add this definition for static void exec pipe and node pointer node. Okay, and so once again, we know that because this is a static function that's defined inside this file, the only way we're reaching this function call is from this switch statement where we already tested that node is going to be of type pipe node. So we can assume safely that this node pointer is going to be its type member is going to be pipe node, and that means its node data is going to be have a left and a right pointer to the two command nodes or other pipes that we might be executing. Okay, so what do we do from here? Well, if we think about what our node has in it, right? So its data is going to be the pipe, and it's got a left and a right, right? So this will be what's on the left and the right hand side of our pipe. And we need to begin those two commands. Well, I want to start from a very simple place first, and then we'll expand out in how we think about this. Right? So let's imagine this left node. Right? So this is, let's just go ahead and set up a pointer node. Left-hand side is this left node. And I'm going to copy that line and do right-hand side is that right node. All right. So we've got these two variables here. And what we might do is something like exec command LHS, right? And exec command RHS. But if we do this, based on our previous discussion, those two commands aren't going to know anything about the pipe, right? We said the first thing that we needed to do before we went off and handled those commands was we need to set up a pipe. Right, so I'm going to make a note to myself here that to do establish pipe. And then we're also going to need to be able to pass some additional data to that pipe, or to the commands on the left and the right hand side to tell it, hey, rather than using standard in read from this pipe, or rather than using the current standard out, which is the terminal, write to this pipe instead, right? So we're going to need to be able to pass some context to this exec command. There's one other nuance here that if we're thinking through this, what if we had a pipe that piped into another piped command, right? So we had three commands that were all connected together via pipes. Well, notice that the way that we're recurring here isn't exactly what we would want, right? So we wouldn't necessarily want to pipe directly to a command. We would really want to pipe to this top level exec, right? So maybe we would just exec left-hand side and exec right-hand side, right? And that would send our recursion back up to this exec. And if right-hand side was another pipe, we would pipe to it just fine, right? So we've got a few issues here that we need to resolve, right? And so let's begin with the contextual issue of how do we establish a pipe that we would then need to be able to pass in as context to a command. So I'm going to set up an array named P, right? So this will be our pipe that we diagrammed before. So int P has two elements in it. And we're going to call the pipe system command, and we're saying establish a new pipe for P in P. So P is now made up of two values. The P read end is P0, and I'll make just a note so that we have it for later. P write is P index 1. Right? So if you remember in the previous diagram, when we saw that file descriptors 3 and 4 were established for the read and write ends of the pipe that we made, if that were the case here, P0 would have been assigned 3 and P1 would have been assigned the integer 4. And so now we need a way of passing this information in, right? We had that clever way that we needed to connect up for our left-hand side. We wanted it to write to P1 for the right-hand side rather than reading from the regular standard in and terminal. We wanted it to read from P0, right? So we need to be able to pass some context in. And we don't really have a good way of doing so, right? So this is a design problem, a software design problem. And we've got a few options, right? We could go redefine what a node is and think to ourselves, maybe a node should carry along with it some information about its file descriptors. But that feels like a weird design decision to make at this point, right? Because the concerns of file descriptors and piping are really separate from the concerns of parsing, which we saw before. And so the product of parsing was this parse tree of nodes. So why don't we establish the context that we're going to need in this execution pipeline as some information that's going to be separate from our nodes. And so to do that, we're probably going to need to, if we want to pass more data to a given function, like this exec command function, and we don't want to change like the implementation of node, well, then we're going to need to add some additional parameters or an additional parameter. And so what is the context we're going to need? Well, we're going to need to establish pipes and we're going to, additional context we'll need. What should I use for standard input? Right, so which file descriptor should I use for standard input? And by default, that will be 0. What should I use for standard out? And is there a file descriptor I should close? In the case of a pipe, of one end of a pipe to close, right? I'll come back and talk about that in a moment because we actually still have some additional work down here that we mentioned in the previous diagram, which is need to close parents pipe ends. And maybe I'll say both of parents pipe ends. All right, so pipe P is still open in the parent process and we'll need to close both of those pipe ends there. We'll come back to that when we think about this, but it looks like the context that we need is going to need to have two integers to keep track of what file descriptor we're going to use for standard input and output, and then whether or not we need to close a file descriptor. All right, so I'm going to suggest that what we're going to do is declare a new type named context. So I'm going to say type def, and this will be a struct context. And we're going to have an integer array of two file descriptors, right? And so this will be for standard in, standard out. And then another integer for fd close. Close and fd, -1 if not, right? So this will be our context type. And each time we go to evaluate a node, we're going to pass this context into it, right? And so this context will say, hey, here's child process that you're spinning up. These are the file descriptors you should connect to standard input and output. Maybe they are already, whatever currently is standard input and output, that's fine. But in the case of piping, we're going to overwrite those things so that we form the connections. And then if there's anything that we need you to close, we're going to pass it in this second member here. All right, so if we have this context, then we need to extend the definition of our functions here. So I'm going to add a context pointer and use the name CTX, which is commonly used when you are passing context around in programs. You'll see the three letters CTX commonly used. So we just changed those two parameters in these two functions, and we need to make sure that we are updating our actual definitions for these two functions to match, right? So, okay, we're going to add our context to the pipe, and we're going to add our context parameter to our command. All right. Great. So now we are able to pass in some context, but when we actually used this function call up above, we didn't have any context to pass into it. And now here's where something interesting is happening. So notice that if we wanted to pass some context down from a pipe to the command that it's going to run, we want to be able to pass that as a second argument here when we go and execute the left node and the right node of a pipe. But we defined this exec function publicly, right? So this is the interface to our exec engine. And this is how we really want this API to appear, right? All you should need to execute some tree of nodes is, hey, give me the parent tree or the root tree of a tree of nodes, and I'll go execute that on your behalf. So we don't really want to change the signature of this function. And when you find yourself in this position where you're kicking off some recursive process and you have a really clean and minimal set of arguments, but the recursive process is then co-recursive with some more nuanced functions that may take more nuanced or specific additional arguments. Typically what you'll do to get around this is say, okay, well, this will be the function that you'll call to kick off the process. But it's very quickly just going to be a wrapper around another function we're going to define internally only, which will be our exec node function. You give it a pointer to a node and a context. And how are we going to define that function? Well, we're going to very quickly just chop up what we've got. So we're going to come back and re-implement exec here. And let's say that, okay, static void exec node is given a pointer to a node and a context. Right? And so this is our internal definition of exec node. And now we have a context that we can pass through. So, okay, let's update our function calls here. So now we have context that we're going to give to our exec command function calls that it is dispatching off to. And great. And so what are we going to do with exec? So this is going to be the function call that comes from our main function. And in the main program, we are execing a tree of nodes. So we need to set up our initial context, right? Before we can go call exec node. So what is our initial context going to be? So our initial context, if we go look at this type def again, is going to have two array elements in it, right? So let's set up what are the first two values of these file descriptors. Well, by default, we're saying when you go to execute a simple command, we just want you to use the file descriptors for standard in and out. We're not overwriting them with anything. We're not doing anything special, right? So we can use standard in file number and standard out file number. Additionally, because we're not piping anything and we don't want you to close any file descriptors when you just by default, we're going to set the fd close member of this context to -1. And now we can kick off this exec node function call. We're going to give it the node parameter as well as the address of this context, right? And so what we've effectively done is rewritten or refactored this exec function to dispatch off to exec node. And in the process, we're setting up the initial context that we're using to kick this process off, right? So now that we've done this, we should be a little bit closer to being able to handle what's going on in piping, right? So in piping, we need to overwrite this context before we recursively say, hey, next command, go run with this given context, right? So we've got two choices here. We can go ahead and set up the context for one of these nodes, and maybe we'll do that first. And then we'll go look at how do we resolve the command and actually use that context to establish those connections. Right? So let's imagine we had piped a piped node, and we've set up the pipe int p. So we've got now handles on those two file descriptors. Okay, so what context do we need for the left-hand side? So I'm going to set up a context variable named left-hand side context, and it's by default going to be a copy of the context that's passed into it, right? So we're making a copy of this. And then what we're going to do is say, okay, left-hand side context, your file descriptor. Remember, this is going to be what descriptors are we using for standard input and output. Well, we're trying to overwrite the standard output file number, right? We're saying, I want your standard output file number, which remember, that's always going to be 1, right? So this is the write end. 1 is what we're going to write to. So the left-hand side is going to write to pipe standard out file number, right? So the inventors of pipe decided we're going to make the end of the pipe that you write to, right? The file descriptor here, the same index in the two ends of the pipe array as the processes file descriptor for standard out, right? So remember what we're saying here is if pipe at index 1 was actually a value of, let's say 4 would be assigned to the index 1 value of the left-hand side context that we're actually going to pass into exec command in order for it to duplicate the file descriptor and connect up or conjoin the pipes and for writing with its standard out. Okay, so we've answered the question of, we've set up this context so that its standard output is going to be connected to the pipe. And now we need to answer this question, is there a file descriptor that should be closed? And in this case, yes. So we want to close the other end of the pipe. So fd close in this context is going to be the pipe's standard in side, right? This is the reading side. So we're going to close that end of the pipe and make sure that standard in is only open on the right-hand side. Right? So we're going to see the opposite effectively of these two lines when we set up the right-hand side's context. All right, so then we set up, we've got our node left-hand side and we go to exec LHS, but this isn't actually what we want to do anymore, right? So we actually, we need to be able to pass in this left-hand side context. We need to be able to give that context to whatever comes next like this, right? Well, we can't do that with exec. Exec was the public top level function that we defined. But this is why we set up this exec node internal function, right? So we can give it a node pointer and a pointer to a context, right? So we're going to make this call exec node. So now we can recursively call exec node and we give it a pointer to this context. Now, out of style purposes, I'm going to rearrange this node pointer left-hand side to come above my context, since that's ultimately is the way that we use the ordering of those as parameters in this function call. Right? So we've got our right-hand side set up and we can do the same things, right? So we're going to need to set up a context for the right-hand side. And that's going to be a copy of our original context. We're going to say right-hand side ctx.file descriptor. And then here we're saying standard in of the file of the right-hand side is going to come from the pipes standard in or the pipes read end, right? And these are intentionally the same value or the same index, right? So someone was intentional in making that the same index of the pipe that you're going to read from is the same index that you would say the file descriptor of a process is going to use for reading, right? That'll be standard in, or index 0 is going to be the read end of this pipe. Okay, we are going to close the right end of the pipe. So we need to say right-hand side context.file descriptor close is going to be the pipe's standard out file number in this case, right? So notice we're setting up this pipe and we're going to be sharing this pipe between these two processes, right? They're going to be connected via these two processes. And I've got a misspelling here somewhere. Right-hand side, okay? And so we do the opposite things, right? We say that left-hand side is going to have its standard out hooked up to the pipe's right end or the pipe standard out end. And the right-hand side is going to have its standard in connected to the pipe standard in. And then we're going to close the opposite end in each of those contexts. Now, what I want to say is that none of this is actually taking those actions, right? This is going to be data that gets passed in to the exec command function, right? So we get this context here. And then once we fork our child, now is when we need to actually act on the context. So here's where we need to evaluate the context and act on it. So what does that mean? Well, remember, the two file descriptors we get are what we want to use as standard in and standard out. So we're going to use dup2 and we're going to say, okay, context fd and then standard in file number. That's going to contain the file descriptor, the index of the file descriptor we want to copy to our standard in file number. Okay? And so if this were a pipe, we would say, hey, read from the pipe, because we set up the pipe up here. If it were a normal command, this would just be regular standard in would overwrite standard in, or actually when you pass the same value to dupe2, nothing happens, right? So it's a no op when two of the same arguments are passed to it. But if we are piping, they won't be the same, right? So here we're going to say ctx fd standard out file number is going to overwrite standard out's file number of the child process, right? So remember, this is all happening in the context of our forked child process before we go and actually execute the program that we're writing, right? So we're making these connections before we dispatch off or command or control to this exec function. The last thing we want to do is close ctx fd close. And so that closes the other end of the pipe that we're not using, if there is one. Oh, and that's right, we don't want to always do this. We only want to do this if ctx fd close is greater than or equal to 0, right? And we're never going to actually use this when it is equal to 0, but 0 is a valid file descriptor number. And our convention was if, by default, if we don't want you to close any file descriptor as part of evaluating or executing this command, we'll give you -1 as the fd close, right? And that's what we set up by default. Okay, so now we're passing in this context to a child process. We're establishing the connections in the child process's file descriptor table based on the context. And then we kick off that child process, and things seem to be good at that point, right? But we're going to have a problem with this wait, right? So we don't actually, when we're piping commands, we don't want to wait for the first command that we execute to complete in the parent process before the second one begins, right? These two processes actually have to be working concurrently, with the left-hand side feeding data to the right-hand side. And those programs are running simultaneously and concurrently with one another. So we don't want to wait here. We're going to need to come back and resolve this, right? But before we do, let's be sure to remember to close both ends of the pipe in the parent's process, right? So in this exec pipe, we left a note to ourselves like, hey, in the child process, we are going to be passing off the right contexts to know which side of the pipe to close. But in the parent process, we actually still need to close both sides of this pipe. So we're going to close P0 and close P1. And actually, if we wanted to use the correct named constants here, we would say close standard out file number here and close standard in file number here. All right. So getting back to this problem of we want both of these exec commands to be working concurrently. We don't want to wait for the first one to complete before we go and start the right-hand side, right? It's important for piping to be able to work out that these processes are running concurrently with one another. So we've got a little bit more work to do here. And I want to return to this diagram where we looked at the idea of we need to return back from commands that we start, or even pipes, how many children processes we should wait on, so that the parent, once it's spun up all of these piped processes, knows how many times to wait, right? So let's rewrite and rethink how we're waiting for processes to complete in our shell example. Okay, so if we are not waiting here, right? We're not waiting an exec command, but we should return the number of child processes that begin in the context of the parent process, right? Well, in this case, we want to be able to return 1, right? One child was spawned here, right? But we can't return 1 from a void function, so let's redeclare this to be an int function. And in fact, all of these helper exec functions are going to need to return int based on this idea that we want to start up these processes and return the count of the total number of processes that we started in order to count and wait on the correct number of processes to complete when we go to exec them. Right? So I'm going to change these 3 helper functions to all return an int value. Right? And you should go ahead and make that change too. And this is going to create some errors in our program because they were previously void, so we weren't returning anything at all. So let's think about how would we make sure that exec node is going to return the number of child processes that begin. Well, The simplest case is probably the case where we have an error or we don't know what to do. We can just return 0 here, right? We began no child processes. In exec command, it's already returning the number of child processes that it's going to begin, right? Which would always be 1 in this case, because this is sort of a base case or a leaf of our execution pipeline. And in exec pipe, it's also going to need to return the number of commands or number of children it has spawned. The interesting and curious thing about exec pipe, though, is because it's recursive, we aren't always guaranteed that pipe is going to begin 2 processes. In fact, at the top of a tree where, let me see if I can find my pen real quick. At the top of a tree where you've got 3 piped processes together. So this would be a command, and this would be a pipe, and this would be another pipe, right? And that would have 2 commands. And so we were piping from this command to this command, and then from this command to this command. Ultimately, this pipe is going to need to return 3 children processes or what it's waiting on. So pipe isn't always going to return 2. We're going to need to be a little bit more clever about how pipe keeps track of the children it starts recursively. All right, so let's go look at exec pipe. So one of the things I just realized is I forgot to update this call on line 59 to exec node instead of just plain old exec, and we're giving it the right-hand side context, a pointer to it. All right. So we got an error here that we're not returning any value at all, even though this function says that it's going to return an integer. So let's set up a variable to keep track of the number of children we've started in this pipe. All right. So int children will initially be 0. Right? Exec node is always going to return the number of children it was responsible for spawning. So we can say children is incremented by exec node on the left-hand side, and likewise, children is incremented by exec node on the right-hand side, right? And so what this is doing is this is taking care of, well, if exec node was going to go and exec another pipe node, it's going to return 2, and then that would be 2 plus however many the left-hand side returned. Well, our left-hand side is always only going to be 1 based on the grammar that we've implemented, but you could imagine, just for completeness purposes, there might be other things you would do on the left-hand side and would want to be careful with that would make it better than assuming it's always going to be 1. Let's just trust the recursive process here. All right, so after we close these things, we can return the number of children that we've spawned. All right, great. So now we are effectively, after we begin these commands and start up our pipe, we're returning back the number of children that each step of our recursive descent on the exec or on the nodes of our tree executed. And what we want to do is wait for that number of children to complete. And where are we going to do that? Well, we're going to do that up in the top level exec, right? So exec node is going to start at the root of our tree. It's going to go down and begin all of these processes of our piped commands. And now what we want to do is just wait on them to complete here. So exec node, we now know, is going to return the number of children that were spawned. And so what we just need to do is set up a for loop. For int I is 0, while I is less than the number of children that were spawned, plus I, and we're going to wait for those children to complete, right? And so we're going to wait the same number of times as there are children nodes that were spun up by our recursive process. So it seems like we've covered our bases and now are passing this context in from one node to the other as we set up the pipe, and we're handling this all recursively. So let's try this out. Let's try saving and making our program and running it. So no errors, that's always good. So we run ls, still seems to work. Well, let's try running ls and then grep for txt or some, I just saw the letters txt here. And what do you know? We've got piping working. And so ls was piped, the ls program or process was piped into, its standard output was piped into the standard input of grep.txt, of grep, searching for txt files. And it was our shell implementation that set up the connection between those two processes by establishing the pipe with a pipe function call and making it work out. Let's see if this will work for even more piped processes. We could try a command such as cat/user share dict words We're going to grep for any word that has O in it and pipe that into the head program, which will give us only the first 10 results. And notice that triple pipeline worked. And what we've done here is your THSH shell tokenized this string. It took those tokens and turned them into a parse tree. And then we took that parse tree and evaluated it recursively, setting up the processes that are, in this case, 3 processes and 2 pipes, and connecting those processes and pipes together in a very specific and clever way that resembled what we did here in this example diagram using system calls. And so your shell program now has piping capability, which is pretty cool. This is exactly how the bash shell is doing piping, right? And by implementing this, you've effectively implemented a simple shell with piping capabilities. I would challenge you, if you want a fun summer project, to try and implement file redirection. You're going to need to extend your grammar to add new tokens for input and output redirection. And you're going to need to add some additional information to your nodes and what it means to start a command, where that input or output redirection is coming from. And then in the process of spinning up a command, you're going to need to be a little bit more clever about how you open a given file and give that file descriptor via the context to the child process. But fundamentally, these things are all related and based on these very simple fundamental system calls. Bringing them all together is a coordinated dance in many ways, right? There's a number of system calls that needed to happen in the correct order here for this to work out. And we were very careful to be sure we evaluated those commands in the order that would make sense. And now just to take one last brief pass through source exec.c, I've reopened it up. And remember, our main program called this exec function with the root node of our tree. So let's imagine we had a piped node at the top that had a left-hand side and a right-hand side of 2 commands, right? So initially some context was set up. We said, hey, standard in is just standard in, standard out is just standard out. We're not going to overwrite anything about those 2 file descriptors. We're also not going to ask any commands to close any file descriptors, because that only makes sense in the context of piping for the way that we've designed this program. Then what we're going to do is we're going to dispatch our recursive process off to exec node, right? And so this is really where we're saying we're getting the idea of that context and we're starting from our root node. Exec node is just going to dispatch off to the specific kind of node that it's trying to exec, right? This is us subdividing our program. We could have written everything in those 2 functions here, but you can imagine that gets pretty confusing pretty quickly. So rather than doing that, we set up separate functions, and we then dispatched off to those functions. And let's imagine we were processing a pipe first, right? So we jumped to the pipe, exec pipe command. And the first thing that pipe did was we made this system call to the pipe system call, right? And so this set up the pipe in the operating system, right? And so if I jump back to that diagram really quickly, that is what set up these 2 entries in the operating system and set up entries 3 and 4 in our parent process, right? So that's where these entries 3 and 4 came from, and those descriptors were connected to those 2 ends of the pipe. We hadn't yet closed them yet, right? And so then what we did was we set up the context that we wanted to call our left-hand side and our right-hand side with. And what is that context all about? Well, we're preparing the file descriptors, right? We're saying the left-hand side, its standard out should be connected to the standard out of the pipe, or the right end of the pipe. And we want it to close the read end of the pipe, or the pipe standard in, right? And then we quickly dispatched off and said, hey, go execute this left-hand side, right? That was a mutually recursive function call that would have brought us back up to exec node, but this time around, we would have been processing a command. That command would have brought us down to exec command. We would have very quickly spun up the child. And before we exec, right? So before we actually turn this child process into another program, what we're doing is we're establishing our file descriptor table, right? So evaluate the context and establish child's file descriptor table, right? And so what we're doing here is we're allowing the caller of this function to give us the context that to say, hey, where should my standard in come from? Where should my standard out come from? And we're just copying that from the context to the specific file descriptor table in this process, right? So once this child began, we set up those connections, right? So if we went back to our diagram, that was us in this diagram saying, okay, in process 1, now that we've spun it up, we're calling dupe2, and we're taking the the right end of our pipe and attaching it to the standard out right end of the process. From there, we did the same thing with standard out. One of these two, when we're piping, is going to be a no op, right? It's going to be standard in is still coming from standard in, but standard out is going to now be the pipe end of that we write to. Whatever end of the pipe in the child process that we don't need to use, we're going to close it to be sure that it doesn't remain open and cause other problems. And then we quickly set up our arguments and called execp or execvp, which we did in the previous video. We return 1 because that's the number of children that this command spun up. And remember, right after this function call happened, this never returned, that function call never returns in the child process. It's now become whatever command we began. And in the parent process, we return 1. That tells us when we return back to our pipe command, children would have been incremented by 1. The same thing happens with the right-hand side of piping that command, but this time around, we're going to redirect or connect the input side of the right-hand side to be the read side of our pipe, right? And then we go do the same thing with the right-hand side. From the parent, once we've begun both of our children, that is when we need to close the file descriptors for the pipe on the parent side, right? The parent no longer needs either end of those pipes, and so we want to clear those up. Then we're going to return the number of children, and that ultimately, in this simple example, is going to bring us back to where we began in exec, and we're just going to wait on those children to complete, right? So in a loop, the first time that loop wait was resolved by one of these two processes finishing, we continued on to the next wait. We were waiting on the second one. Once both of them completed, our program continued on, and we could once again type into our shell. This was a fast-paced and a lot of content packed into a single lecture, but I wanted to bring you all to a command line shell that had not only simple command execution, but also piping. These are concepts that you'll explore in more depth in operating systems, which is a class that if this stuff is interesting to you, I think you'll love. And if you enjoyed the parsing and the tokenization side of things and thinking about how we can create structures that we can then compute with, compilers is also a great course that I think you will look forward to in the upper division computer science classes. Great work bringing this together. This is a very non-trivial program to have written in C in Comp 211.